Okay, so in this video we have a commutative ring B with maximal ideal P, and we want to show that the quotient B over P is isomorphic to this quotient here. So we're going to recall a couple definitions. If I have a commutative ring R with a prime ideal Q, the localization of R at Q is the set of fractions where the numerator is an element of R and the denominator is an element of R minus Q. Okay, so whenever you have a commutative ring and a prime ideal Q, you can talk about this construction. So that's what we're referring to here by BP. This is the localization of B at the ideal P. And then the ideal pBP, this is the ideal lying above P. And this is just the ideal generated by these products. Okay, so it's sums of products where the PI is in P, and then the RI over SI is in BP. So it's kind of like the smallest ideal of BP that contains the original ideal P. Okay, so now that we have those definitions, our proof, we're going to let phi from B to this quotient, so BP over pBP. This is going to be defined by, so if I have a B in the ring B, I'm going to map this to the coset. I'm going to map it to B plus pBP. And, technically this should say B over 1 because sort of in our target ring, everything is technically a fraction, but we're kind of just thinking of this as the original B. It's kind of like the embedding of the original element B into the ring BP. Great. So we want to show two things. First, we want to show that the kernel of phi is equal to P, because then we can use the first isomorphism theorem to show that there's an isomorphism between B over P and then whatever the image of phi is, right? And then the second thing we want to show is that phi is surjective. Okay, and if we can show these two things, we'll be done. So for the first claim, we want to show that the kernel of phi is equal to P. So we're actually going to start by assuming that P is an element of the kernel of phi. Okay, so then by definition, phi of P is equal to 0, which in the case of this quotient ring just means that this coset is equal to pBP, right? Because if you're equal to 0 in a quotient ring, that's the same as saying that that coset is just equal to the coset that you divided by, or it's equal to the ideal that you divided by. Okay, and then this is equivalent to saying that P is an element of pBP. Great. So then, what does it mean for P to be an element of this ideal? It means that there exists, we can call them P1, pk, and these are elements of P, and there exist R1 over S1, RK over SK. These are in BP, such that P is equal to this sum. It's equal to P1 R1 over S1 plus dot 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 PK RK over SK, right? Because like we said before, this ideal pBp, this is generated by elements of BP that are just a product of something in P, like these PIs, and then elements of BP, general elements of BP. Okay, but we know that each of these SI, right, so each of these SI is in B set minus P. And so that means that none of them are equal to 0, right, because P is an ideal and it contains 0. So what we can do then is we can just multiply out the denominators. So we can multiply out all of the SI. So we can write S1 times SK P is equal to P1 R1. And then if we multiply by S1, S2, dot, 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 SK, we're going to have a product here. So we're going to have S1 times S2 times dot, dot, dot times SK. And then we're going to divide out the S1. So we'll just call that T1, right? So Ti is defined to be S1 dot, dot, dot SK divided by SI. Right, so we have T1 here, and then we can keep going. Here we're going to have PK RK times TK. And what we want to notice is that now this thing on the right is just an element of P. Right, so we originally had an element of P times BP, but we multiplied out all of the denominators. And so now we have something that isn't really a fraction anymore, so it's just an element of P. Great. But we also know that P is a prime ideal. So since P is a prime ideal, this product, S1, SK, P, which we know is in P, we know that one of S1, SK, P is contained in P, right? Because if you have a prime ideal, if a product of elements is in the ideal, at least one of the elements has to be in the ideal, just by definition. Great. But we know that, again, just recalling the definition of the SI, that none of these is an element of P. And so therefore that forces P to be an element of P. Right, because we started with these fractions that look like Ri over Si, and these are contained in the localization at P, so that forces the denominator to not be in P. So that shows that P is in P. Great, so we just showed that the kernel, so therefore the kernel of phi is contained in P. And so now we just have to show the reverse inclusion. So now let P be an element of P. And notice that phi of P, again, by definition, this is just P plus pBp. But P is an element of the ideal P. So P is definitely an element of pBp, right? Because P is just equal to P times 1. And so that gives us that this is equal to pBp. Great. So this proves the first claim, right? This proves that the kernel of phi is equal to the ideal p. And so now the only thing that remains to be shown is that phi is surjective. Okay, so now we want to let R over S plus pBp, we want to just let this be an arbitrary element of this quotient. And what we want to do is we want to produce some element of B, right? So we want B in B such that phi of B is equal to this coset. So this will follow if the following holds. If R over S plus P is equal to B for some P in the ideal P. Right? Because if this is true, then the coset R over S, so R over S plus P plus pBp, this is equal to R over S plus pBp, because P is an element of pBp. And then this is equal to B plus pBp, right? So we want to argue that we can find such an element, P. Great. So, but what do we know about the ideal P and then the ideal SB, right? So what do we know about the ideal generated by S in the ring B and what you would get if you added this to P? Well, we know that P is a maximal ideal. That was what we used to show that that the kernel of phi is equal to P, right? And so we know that if we add another ideal to this ideal P, as long as the ideal is generated by something that isn't in P, right? This isn't in P. So we know that this is an ideal that strictly contains P, and so that forces this to be equal to B, right? Because P plus SB is an ideal. We know that it contains P, and we know that it's not equal to P because S isn't an element of P. And so this is equal to B. Right? So therefore, there exists P in P and B in B such that the following is true. So R is equal to BS minus PS, right? Because we're thinking of R as being an element of B. So R is in B. BS is an element of the ideal generated by S. And this number here, negative PS, this is an element of P. Right, and so we're just using this fact that we just showed here that the sum of these two is equal to B. Okay, but then if you divide by S, so now we're thinking of these as fractions, if you divide by S, you get RS is equal to B minus P, and then that gives you that R over S plus P is equal to B. right? And so we found an element B and an element P so that this is true. And so that means that the thing that we wanted to have happen is true, which is that phi of B is equal to R over S plus P BP. Great, and so we showed that phi is surjective and that its kernel is equal to P. So therefore, we get that B divided by the kernel of phi, which is P, is isomorphic to the image, which is this ring. And that is what we wanted to show. Thanks very much for watching.